Good afternoon and welcome to the latest BitGardener webinar. My name is John Kowalski. I'm part of the marketing team here and I'd like to welcome you. Today's topic is media milling deep dive. This is the second part of our dispersion series. The first part is actually going to be held next week. There's a link in the chat if you'd like to register for that. The order got messed up a little due to some scheduling conflicts, but also, yes, it is Thanksgiving week next week, so a lot of you may not be working, but if that's something of interest, go ahead and register anyway, as you'll receive the link to the recording. Today's presentation will last about 45 minutes roughly. Our presenter is our Director of Dispersion, Managing Director of Dispersion for VMA Getzman and also BitGardener USA here in the US and Canada. His name is Andreas Stummer and has a wealth of knowledge. One final note, if you have any questions during the presentation, please log them in the chat box located in the bottom right-hand corner of your screen. Time permitting, we'll get to them. If we do run out of time, Andy or someone on his team will follow up with you directly. We are also recording this, so immediately following, you'll receive a link. Feel free to watch it at a later date, share it with colleagues. I hear it's great for date night too, so whatever you like. So with that, let me introduce Mr. Andy Stummer. Andy. And don't forget I muted you, sir.
Thank you, John, for the nice introduction, and welcome everybody to the Media Milling Deep Dive. I appreciate everybody that's joining us today, and we'll dive right in. So basically, we're just going to do a quick introduction about the company, who is VMA, and the relationship with BitGardener. Then we're going to do a brief overview about the actual dispersion process. There's always two steps. We have our pre-dispersion process, and then we also have that milling that we're going to talk in more detail today. We're going to cover some different types of laboratory scale as well as production equipment. We have some lab space in Wallingford. We're going to cover that as well as in Germany, our capabilities. And also a little bit about the quality control aspects of the equipment. So here you can already see kind of like giving you a good idea of the entire product line, everything from lab scale all the way up to manufacturing. You can see some of them have basket mills attached to them. Some of them have dissolver discs, basket mill, dissolver disc, basket mill. So all of these units are basically have a modularity approach to them. That means that they have a quick change system that you can swap out. Each of these machines can be used as a dissolver or as a media mill or rotor stator or vacuum system, depending on how you configure it. There's many different options of how you can accessorize the disper mats. That's what kind of sets them apart from the competition. And that was the vision that Hermann and Elke Getzman had when they founded VMA Getzman in Germany in 1972. The good news is that business is still in family hands. So it's run today by the two kids. Christian and Martin are running the company out of Reichshof, which is about 30 miles east of Cologne. And just a quick background. So BIC was one of the first customers of VMA disper mats in Germany, BIC Chemie. And basically, they brought some of these dispersers over to the US and had them run in the lab up in Connecticut. And they brought customers into the facility to show them around. And a lot of customers that came in were really impressed by the quietness and by the efficiency of the disper mats that they saw. And they were asking if there would be any way that they could purchase these models. So that's when the former CEO at BIC made a decision that he would include or bring in the VMA Getzman product line to the BitGardener product portfolio. So since 1988, we have become the exclusive distributor for VMA Getzman disper mats in North America. So that's kind of like a quick background about the relationship BIC and VMA. So we not only are the sales arm for VMA for North America, but we also do all the service, installation, marketing, and everything else. We have 8 salespeople out in the field covering the entire United States and Canada. We also have representation down in Mexico and Latin America for the same equipment. The company itself has about 100 employees scattered all over the world. They have one nice production area in Germany. And you can see a picture right here. So basically that building in the middle was added on a couple of years ago during COVID. So we actually have more production and design capability than we did before at VMA, and that allows us to turn around the products quicker and also really customize a lot of these solutions. So 40% of all the disc mats that VMA manufactures are customized. So a lot of customers, especially new markets, new industries, like think of batteries, lithium ion, different types of, hydrogen applications for these electrolyzers. They are very specific on what that those slurries can get in contact with. So a lot of these disc mats that are built have custom materials. Some of them are plated with gold, believe it or not. We have some very high-end applications that require some very unique materials with our disc mats. We also have one big company that make platinum pastes. They're all custom machines. So it's really, really interesting on how many different end-use markets are out there and how much customization really can take place with the disc mat line. So the big question is always, why are we really dispersing, and what is the dispersion process, and why are we milling? So the whole idea is to get a better looking product, right? And when we are actually dispersing, we are introducing shear forces to our slurry. And either it's done through a disc, it's done through a cow's blade. So depending on whether we're pre-dispersing or milling, but we're always putting in shear forces into our mill base. And the whole idea is really to break up the binding forces. They're also called the Van der Waals forces that hold these pigment particles or nanoparticles together and basically create these larger clusters called agglomerates. And then what we want to do is we want to break up these binding forces, these invisible magnetic forces, and separate them. And that's the whole idea of dispersing and milling. We're not trying to destroy any pigments. Or particles. We really just want to break up these Van der Waals forces. That helps us then to really get down to the primary particle size, which then in turn will help us get much better color strength, better gloss. Our overall appearance is improved, especially with coatings. Automotive is very big on reducing the particle size as small as possible. It gives them a very good looking paint. And that's what the customers are looking for. So the key here is better visual appearance. And in return, by being able to reduce particle size, we are now also saving money because we have much improved pigment efficiency, which will help us save, of course, raw material costs. And another advantage of doing a proper dispersing and milling job is that we get better product consistency. That helps us also improve our formulations. We need to maybe cut back on the amount of pigment that we are putting in, which again is pigment efficiency and always related to cost savings that everybody's looking for, especially in times like we're in right now. And then we're looking for obviously consistent particle size distribution. There are different measurement technologies that can point that out. Particle size analyzers, you're probably familiar with some of these technologies that will then quantify that consistent particle size distribution if we're doing a good job with the dispersing and milling. And all of that should help us create better batches in manufacturing, which means we have better upscale results because of our dispersing and milling when it's done efficiently. Now, there are also issues if you don't do a good job doing the dispersion process of pigments, for example, right? You'll see it immediately visually. The color is not going to look as bright. You're going to have poor stability of the product, flocculation of pigments. That's usually a big part of it is formulation related, and we'll touch on that a little bit. But formulation additives is really critical if I want to have a very good dispersion when I'm done with my milling process. So it's really critical to have proper additives in the formula. Our sister company, Big USA, obviously, most of you are probably very familiar with them. They have some really good products that can help us keep these pigments in a suspended state so they don't flocculate back together. Sagging, leveling, settling, some key terms here. Obviously, reduce gloss or not on here, haze levels, and then separation. It's just some of these issues that come up when we improperly disperse our pigment slurries. So here's a good example. We ran a product, and on the left side, we show you a pre-dispersed product. So we would just use a cowl's blade. And on the right side, we show you a fully milled product. That was actually done with the basket mill. And you can see that on a Hegman, how different they look. So really, a lot of times, customers want to save time and costs, and they think that they can get by with just using a cowl's blade. But the truth is, unless you're happy with an inconsistent, poor quality product, you'll be much better off really using milling technology after you're done using a cowl's blade. So that there are some things that are really important here is that, stability of our product. So, pigments have to have a very good, strong color fastness. So that helps them to with the fading over time. Brightness is another, outcome of a very good dispersion. So that will give us usually the best looking color. And of course, the smaller we can bring down our particle size, the better color we have, the better will be our transparency. And that, as I mentioned earlier, cost is a big driver because it then allows us to use less of the very expensive pigments in our formula if we do a good job reducing the particle size. And then usually viscosity is another important aspect here because we want to be able to process the material. And if the viscosity is really high, sometimes it's difficult to bring or move the material through the media mills. For example, with basket mills, we can't really mill anything that's too viscous because the pumps won't be able to draw the material into the basket mill. So viscosity is really critical. Usually we're looking here for a sweet spot anywhere from 2,000 to about 8,000 centipoise. We can work with lower and higher, but this viscosity range is really good for putting in the right amount of energy that helps us breaking up these binding forces. If our viscosity was super low, like water, then it's very difficult to put in a lot of energy. So we have to disperse or mill longer to really get to the particle size that we're looking for because it's just more difficult to put in the energy needed. So therefore, we want to maybe change or look at the formulation to bring up the viscosity into that nice range. We were talking 2 to 8,000 centipoise. That really helps us there from an energy standpoint. Okay, so it's really important to remember that, again, we are not trying to destroy our particles or pigments. We are really only breaking up these binding forces. That's all we are doing. And we're turning these agglomerates into aggregates when we use a cowl's blade. And then if we do the milling, we then reduce the aggregates down to the primary particle size. The shear forces are responsible for that separation. That's the only thing that helps us there. And then obviously, again, the additives play always a critical part in a good functioning and good looking product. It's just an example of the different types of pigments, what that looks like under a microscope. Most of you probably know, but those of you that don't, that's kind of what that looks like under the microscope. And we just want to be able to break up these binding forces and make sure that these particles then are separated in the dispersing and milling process. This slide, I think, is really well done. It explains kind of like what we're doing. So we have these larger blocks, like over here, these cubes, and they're fused together. And these are basically primary particles that are all clumped in larger clusters. We call these large clusters agglomerates. And then when we take a Cowles blade and we expose these agglomerates to our Cowles blade at a high tip speed, looking there between 18 to 25 meters per second, which is an optimum pre-dispersion tip speed, that will then allow us to pull in enough shear to break up the binding forces and reduce these agglomerates to smaller particle clusters we call aggregates. Now, from the aggregate level to get down to the primary particle, to separate that, a Cowles blade is no longer sufficient. Therefore, we need to use a media mill. You cannot go from an agglomerate down to primary particle size just using a Cowles blade. It's not possible because we are usually topping out at about 10 microns of particle size if we are only using a Cowles blade. So among other things here, we're also wetting our solid particles. And then again, we try to stabilize the smaller particles in our slurry by using the right type of additive in our formulation. So this kind of shows you the process here. You have your Cowles blade first for wetting, pre-dispersing, so de-agglomerating our larger particle clusters. And then when we reach the aggregate size, which is a threshold of 10 microns, so the range is about 10 to 30 microns, depending on the pigment or the formulation. And then we are actually milling, and there we are able to bring down the particles to primary particle size. So this slide is actually interesting because it kind of shows you the breakout. So we start with the dissolver, and then at about 10 microns, we start medium milling. And so there's different types of medium mills. We have some of you probably familiar with, old school 3-roll mills. It's kind of like older technology that's being replaced now with more efficient milling systems, like the basket mills are fantastic. We prove that out in our lab on a weekly basis where we have customers come in and, we had one customer for specific ink formulations. They were doing everything on a 3-roll mill. They were milling for 18 hours on 3 different pigments to bring down the particle size. And by changing it over to a bead mill, to a basket mill in that case, we were able to do that whole job in 45 minutes. So you can imagine the excitement there and the amount of cost savings just by going and changing the process is really, really huge when it's done the right way. And then with the bead mills, we're able to go super small. Also, we have, some applications where we want to go below 150 nanometers. And with the bead mills, with the right bead mill design for nanoparticles, that is easily achievable. But you need to, of course, again, have the right setup. So critical to remember here that dispersing is a 2-step process. So we have our pre-dispersion process where we use the Cowles blade, again, 18 to 25 meters per second, and that is done with the dissolvers. And then we have our media milling or fine grinding or dispersing, fine dispersing, where we are reducing our milling speed, the speed of our milling disc or rotor. We're reducing it down between 10 to 16 meters per second. And there we have our vertical mills. We have what's called an APS system, stands for air pressure system. I'll show you that in a little bit. We have our basket mill system called TML, and then we also have horizontal medium mills called SL in the lab space and RS in the manufacturing arena. Just briefly, for this pre-dispersing, it's really critical the vessel size, the 1/3 diameter ratio to vessel diameter still holds true today. So basically, you can see that on this graph right here. Try that the blade diameter is about 1/3 of your vessel, then you're optimizing the ratio. Of course, depending on the viscosity of your material, that can vary. So that picture on the table on the right-hand side kind of shows you the volume of the container in milliliters. And then you can see, depending on the viscosity, the disc diameter that you could use with that type of a container or container size, So if you have, let's say, 1 liter container, you would be optimizing probably to start with the 50 millimeter blade, and then you kind of see what's going on and kind of work from there. Usually that pre-dispersion process shouldn't take any more than 15 to maybe 30 minutes. And then you should have a fully pre-dispersed material that is then ready to be milled with one of the different medium mills. So this is a good formula. It's the tip speed formula. So here basically you have your RPMs. You multiply that by pi times the diameter of your dispersing or Cowles blade. And if you want in meters per second, you express the diameter of the dispersion blade in meters, and then you divide everything by 60. So if my blade diameter, let's say, was 50 millimeters, then I would express that as 0.05 times 3.14 times the RPMs, let's say 2000, and then you divide everything by 60. And that would give you an accurate number for the actual tip or peripheral speed of the blade in meters per second. And you want to be there between 18 to 25 to optimize that pre-dispersion process. The formula is exactly the same when you're calculating milling disc speed, except you're reducing that speed and go between 10 to 16 meters per second. Here, this is the donut, very nice a picture of what you can actually see inside of the pot if you have the optimized tip speed and also the right viscosity range. You should look in there and you should see that beautiful donut being formed. That will give you the indicator that you're doing it the right way. So 15 to 30 minutes for your pre-dispersion, the donut effect, again, tip speed, 18 to 25 meters per second. Geometric consideration, again, blade diameter, depending on the size of the container. The viscosity, you can move it up or down. And then there's different types of Cowles blades or impeller discs with different set of teeth, or different angles. There's a lot of custom discs out there with different materials, ceramic, coated, Teflon. So depending on what you're trying to disperse, there's many different options from a design aspect when it comes to the Cowles blades. The volume of the mill base should be about 50%, not exceeding 70% or less than 40% in the container, or you're spilling or you're not able to oscillate properly. So 50% fill rate is what we recommend. The right pigment fill concentration, of course. Try to keep the temperature as low as possible, because when we're dispersing, even with the Cowles blade, we're putting in energy and we are increasing the temperature automatically through that process. And then additives, again, critical, important to maintain good product consistency and that you don't have reflocculation of the pigments post milling. And then look at the particle size, do a Hagman after the pre-dispersion results, look at where you are. And then if you are completed with the pre-dispersion process, move over to the media milling to actually get down to the primary particle size. So with the dissolver, we're able to just put in a limited amount of energy because we only have a blade, we're not using media. Again, it's only for de-agglomeration, not to go from aggregate to primary. But it is a critical step. It's important. We're also wetting our pigments. We make good use of the additives that are in there. We're homogenizing everything. It's really important that you do this properly and don't forgo it and go straight to a mill because you would have issues there with clogging of the screens or dynamic gap. So we really need to be sure that we are in a workable pigment size, particle size range before we start milling. And usually that threshold is about 10 microns. And then again, just to conclude that again, if you stop at the dissolver, remember that one slide where you saw the drawdowns, where one was really, with streaks and just didn't look good. That's what happens if you stop at the dissolver stage. And when we are milling, we are able to put in a lot more energy down to primary particle size, and we'll get a really clean looking, really beautiful product if we have a good formula. So with that, we're gonna take a quick look into the actual mill, what's happening inside. So obviously we have a rotor, a milling disc, and then we have beads. And as we are basically turning up the rotor speed or the milling disc speed, these speeds start to, drift around and basically inside of that milling chamber or basket at very high speeds. They move all over the place. They impact the sidewall of our media mills, the rotor. They wear everything down over time. So the choice of proper, rotor material or, maybe even ceramic line milling chamber to reduce the wear of the equipment, it becomes very critical because there's really a lot going on inside of our mill. And so as these medias, or these balls, these grinding balls or beads start drifting towards each other, or impacting each other. Right before the point of impact, you can see on the top picture where basically that force is causing these particles to shear off. And that is actually what's happening inside of a media mill. So contrary, a lot of people think, hey, when I'm milling, I'm actually crushing my media or my pigment particles or other particles in between two balls. That is actually a very unlikely thing to happen. Probability is very small. Why is that? Think of that when you were a little kid and you sat in a bathtub and you were trying to play with that rubber duck and you were trying to catch that rubber duck with your hands. What happens as you put your hands closer together and right before they touch, that rubber duck always got away. And that's exactly the same thing that's happening inside of a bead mill. These balls, the media beads that come together at very high speeds, actually have so much force that they are really breaking up these binding forces and are pushing the particles away. And through that shear motion, we are breaking up these larger particle clusters and reducing them to smaller and smaller particles until we get to the primary particle size. So that's really what is happening inside of a media mill. Okay, so that's really important. Now, of course, there is a chance that you will have one pigment particle or another particle just floating right by it and get pushed right in the middle, and it could get crushed. But the probability And there's actually equations that Dr. Quade did. I went to one of his presentations. He's one of the most renowned milling experts out of Germany, University of Braunschweig, and he has studies and very complicated equations that kind of speak to that, that kind of detail exactly what happens in the mill and the improbability of an actual particle getting destroyed by impact because of that fluid dynamic motion that's going on and pushing the particles away. So that's what's happening inside of the bead mill. Then again, what makes a big difference there is the type of media that we are using. So we always want to recommend use higher grade beads, meaning zirconium oxide, yttrium, or serum stabilized. There's a number of different beads. Use the right size. We can talk about that later, but bead sizing becomes an issue. But if you start at 10 microns, usually 1 to 1.2 millimeter bead size should be good. And then use the good quality zirconium oxide beads. You can see, compare that to a glass bead. The specific weight is 6.1 compared to 2.5. So it's almost 2.5 times harder. Heavier than a glass bead. But if you look at the wicker hardness, it's almost 3 times as hard. So what happens if you use glass? The most beautiful thing is you save money initially because glass beads are a lot cheaper than zirconium oxide beads. But that's kind of where all the fun ends right there for you, because the glass beads will wear quicker. They tend to break up. You'll end up with shards in your mill base that you have to filter out. But more importantly, you're going to find they work very unevenly, and then you're going to have a lot of fines and not the correct size of glass beads inside of your milling chamber. So you'll have to do constant filtering, screening, and it's very tedious and also expensive process because it takes a lot of time. And also your milling efficiency goes way down because the beads are not as heavy, so you need more time. Your kinetic energy is reduced, and then obviously they're not as hard. So that is not ideal. So we don't recommend glass beads at all. We always recommend to go with the zirconium oxide beads. That's what we use in our lab space. And that's where we see the best results with our Dispermat equipment is definitely the zirconium route. On the bottom there, you kind of see the different media sizes going. We even have them smaller. There is nano ones for nanomilling. They start at 0.1 millimeter, like a micron, and then up. We offer them from 2.8 to 3.3 for very large particles. But usually we start, if we do a good job pre-dispersing at 1.2 to, actually we offer 1.4, 1.5, 1.2 to 1.5. They used to be to 1.7, but we don't offer that anymore. That's a very good starting point. And then we can really efficiently mill down from about 10 microns to about 1 to 2 microns very quickly on most formulas, and then even down to 600-700 nanometers with the same bead size. And if we want to go smaller with our primary particles, then we really need to start reducing the media size, and we go down progressively as we see our particle size getting reduced also. That's important to remember, is that we need to also go down with our media size as we're getting smaller. Now, this is important, is the influence of our bead weight, right? So if I look at that nail, and it's kind of the same thing what's happening when I'm milling. If I take a large bead or large hammer, I drive that nail in with one blow. But if I change the weight of my hammer, it can take me more impacts, right? If I'm reducing the size of my hammer, I can go from one impact 10 to maybe 100. So the weight is really critical with my kinetic energy. So always use higher specific beads with high specific gravity. That's why zirconium is much better than glass for that principle alone. That's a formula. You may want to write it down. I don't really use it because we know the beads that we are using, but some people may want to calculate that. So here's your formula, and we will share the presentation, and you can write that down or download the presentation and then copy it from there. Okay, so here is another slide kind of showing you what we talked earlier. So you have these larger beads right there under the microscope, and then we have the pigment particle on the center left, and then on the center right is that sheared particle cluster that now we are reducing that larger aggregate to primary particle size. And it's happening actually as the beads collide. Right in that corner is where that shearing takes place, and a lot of that force is created that's causing that shearing of our aggregate, and therefore breaking up these van der Waals forces and reducing our particle size down to primary particle size. So it's very important then to keep in mind that after we are done pre-dispersing, again, we want to be between 10 to 30 microns of particle size. Bead weight and size, we just talked about that. The type of bead, we covered that. Zirconium oxide, highly recommended. The bead volume depends on the type of milling system that we use. The amount of beads, the shape of our beads, always make sure you screen your beads. Not every time if you use zirconium, but periodically to get rid of the fines and then replace them with new beads, so always have good quality. Bead loading, tip speed, we talked about that, 10 to 16 when we're milling, meters per second. Product temperature, critical, especially when we're milling, we're putting in a lot of energy. Therefore, we want to cool it properly. Double wall containers, double wall supply vessels, double wall milling chamber, double wall milling basket becomes very critical when we are milling. So temperature control is very, very important. If you do not have it, you cannot properly mill because the temperature will go up very, very quickly. And if you are running solvent-based products, it gets even more critical because you'll evaporate all the solvents very rapidly, and it could also pose a danger because the temperature will go up very fast. Milling time, obviously, there's really no rule there. And we have seen going from 3-roll mills to a basket mill from 18 hours to 45 minutes. But we have also seen some instances where, we use a basket mill in some specific application. They milled for 2-3 hours. But really extensive, long milling times overnight, we don't really see it. But depending on your formula, some mill quicker, some take longer. Again, we talked about that earlier. Viscosity is critical. Try to stay within 2 to 8,000. That's usually a sweet spot. And then the diameter of my milling tool, my rotor, or my milling disc. You don't have a lot of options there because the milling chamber and the rotor kind of work hand in hand. So there is fixed ratios and also fixed bead volumes usually, so you don't have really a lot of choice. But if you increase the milling tool diameter, you also increase the milling chamber size. So you basically would mill faster or mill more material. Type of material critical, ceramic, very popular. The reason is it's very hard and also very resistant to abrasion. Stainless steel on a standard configuration will wear over time. So you'll end up with the metal bleeding into your slurry. So therefore, if you're making a white product, it could turn gray if you don't use ceramic and you're milling for a long time. Then you would definitely see bleeding from the milling chamber or the stainless steel rotor into your slurry. And we actually have seen it where beautiful white looked gray when they were done milling. So everything had to be changed over to a ceramic rotor, or at least a ceramic milling chamber. And then the design of my media mill. So we have the vertical, horizontal, or basket mill design that plays a role in how we're going about the business. So here is that Dispermat modularity I referred to in the beginning. You can see we have one standalone Dispermat. This is just one example. I think this is the Dispermat CV4. No, sorry, this is actually the CA, I can tell on the motor head. And then all these other pictures basically show you these different attachments that will fit right onto our CA in this case. So we can add a rotor stator. We have a vertical bead mill on the bottom left that's called the APS. We have a wall scraper system for very viscous materials. You can't use that when you're milling really, because when you need to use it, the material probably is so thick that it won't go through your basket mill, and you can't use it with the APS. So that's for pre-dispersing, really thick paste. We also have a vacuum system. We have the basket mill on the bottom right, called the TML. We're also making TMLs now with vacuum, and the reason is that some people, or more and more people, are finding out that their milling efficiency improves a lot by using vacuum, because we're removing the air from our slurry. And if you think about the air, these are tiny, small little air bubbles, and they are basically acting almost as little mattresses, and they cushion the blow of the media. So therefore, your milling will take longer, and your milling efficiency is reduced if you have a lot of air bubbles inside of your slurry. So by taking out the air, I'm improving my milling efficiency. I get there faster to a satisfactory end result. And I'm also able to quicker transfer then my material, my melt material, from one container to another. This becomes very prevalent in the manufacturing cycle, where sometimes it takes a long time to move from one container to another when I'm done milling, if I have a lot of air inside of my my mill base. So here is just an example of the lab dissolver there. They can go up to 20,000 RPM, so very, very high. Again, this modularity, we have explosion-proof models, and then this model here has the C technology package for data processing, upscaling, storing of data points, storing of batches, so you can actually replicate the process every single time, and ensure that you're getting very, very good repeatable results. If you have to calculate everything by hand, you can do it, but it's getting then becomes more of a variability in your process. And by having very good tight process control, I can exclude that, and then that would help, with the manufacturing of my product, or R&D processing. So again, just to summarize that, so we can use a Dispermat as a homogenizer, emulsifier, or disperser, and depending on what you're trying to do with the different attachments, so you have the different options here. Okay, so kind of like a quick view on the basket mill, tourist mill TML as it's called. So we have that all the way from lab scale to manufacturing, a very interesting piece of equipment because it gives you excellent milling performance, very quick milling performance, easy to clean. We have competitors that have similar mills, they call immersion mills, and we've seen them with screens on the side. We purposely opted against that design philosophy for a number of reasons. First of all, this is where you don't, on that slide, you can't see the beads in here, okay? You just see a milling disc and the pumping wheel on top. The yellow is the pumping wheel, and then the milling disc is right below. That chamber is filled with beads. When you're milling, that milling disc is working really hard to get these beads moving inside of that milling chamber. And that, if the screen was on the side, would impact these beads, the media would impact the screens very, very often, very quickly, and very hard. Means you have, excessive wear of your screen because of the design of the mill. And also, this is where I'm putting in all my energy. That's where I'm creating a lot of heat. So I want to have this chamber double walled. So you can already see my cooling channels right here, where other designers have a screen. We don't. We have cooling because we need cooling there. And then we have our screen on the bottom where it is not, exposed to so much wear. And right below the screen, we have a cow's blade that helps us draw the mill base outside of the basket and then pump it back around to the top, where you can see that very nicely right here. And then basically very nice milling action in and out of our basket. So the cow's blade does a good job. And then the pumping wheel will suck the mill base back in. And you can see here, we're showing the beads on this graph on the left. And then on the right, we're just taking it out and showing you the finished product. This is a manufacturing scale TML, beautiful polished steel. Again, we have 3 bars that are holding the basket. So the one, of course, the left basket or the right bar, coolant in or water in. On the left, coolant water out. And in the back, we have another bar. That's where actually our temperature sensor goes in, and we measure the actual temperature inside of our basket. So we know always what is happening there, how hot is the material getting, and are we efficiently cooling. So that's really important. The screw right there is only for the bead filling channel, and that's where we basically put in our beads on the manufacturing side. Again, we can go from very small volumes up to 2,000 liters. We have, with the C technology and with our TML concept, very good upscale ratio, almost 1-to-1. Very easy to clean our mills. What's also very attractive is the design of our Dispermats with that quick change system, where we're able to just put on different attachments. So what customers are doing that, running different color families, they're just buying different baskets, and they dedicate these basket mills for the different color families, and then they just use them as they need them for running a different color. The advantage there is you're not tying down the equipment for cleaning for half a day. You're just swapping the baskets and then running it again. So that's one of the huge advantages of the Dispermat over some of these other milling concepts that are out there. Here is an example of a customer that's using the Dispermat TM in manufacturing. So the interesting concept here is that we have both. We have a Dispermat and a medium mill already in one. So you can see the basket is right on top. Right below, we have the shaft. And then the cow's blade is behind the gentleman in the gray sweatshirt, is where that blue drum is. You can see the cow's blade leaning against the drum, and they're not installed yet. But basically what happens here is you have your container, you put the container underneath the TM, you add your raw materials, either you do it there or somewhere else where you can weigh it out properly, and then you start the pre-dispersion process with the blade. After about half an hour, or depending on what material you're running, you then can go and push a button on the control panel, and the basket comes down, and now you're milling. So you don't have to move the container around. Everything is done in one location on one machine, in one continuous process. So that's a huge advantage for customers trying to save space in your manufacturing environment and have a very, very clean and efficient milling cycle. And then we have the APS mill here. Basically, this is more for the lab. This is not really manufacturing. So you have 2 containers, top and the bottom container, and you are milling or pre-dispersing first in the top container with the cow's blade. Then you swap out the blade for a milling disc, you add beads, and then you pull down the cover. See that on the right? You close it up. There's a clamping ring that goes around it, and then you're milling. On the bottom of the top container, you can see it here is actually, you can see it here is a screen that separates basically the media from the container on the bottom. And there's a drain plug in there also. So when you're done milling, all you do is remove the drain plug, hook up an air hose. There is a socket. You can see that on this picture on the right-hand side in the cover. It's an air socket, and that is only there to pressurize my APS system and purge out my mill base through the screen into my container below. So that basically is a very, very efficient way of milling. Many samples, very small volume inside of my laboratory. Not really efficient though when I'm trying to make production scale batches, because I would need a lot of media. We can add the same amount of media as we have material in there. So if I am running 500 milliliter of material, I can add 500 milliliter of beads. Now I get very good milling efficiency, very fast milling. But if I'm trying to do this with 2,000 liters, I'd have to put 2 tons of beads in there. It would be, cost prohibitive. And also, how do you handle that many beads and that volume? So this is really a great design for the lab, but unfortunately not really scalable. So then we have here just a couple pictures of our horizontal mill design. So we have the SL, beautiful machine, also with the C technology here. And then we have the RS, which is our production scale horizontal medium mill. You'll see here on the picture on the left, the supply vessel. There is a pumping and steering system with a motor that sits right on top that actually forces our mill base into the milling chamber. And then basically the material would circulate back and then come up and back into our supply vessel. So very good circulation of our mill base in and out of the mill. And you can also do pass through. So if you want to just go one cycle, you're done, or move it to another mill. Some people set up numerous horizontal mills in succession. So they go from one mill to another mill to another mill. And the only thing that changes will be the screen size and the media size. So they basically go progressively smaller if they want to really have very fine material and they don't want to swap out the beads on one machine. So that is a way of getting down to very, very small particles very efficiently, but may not be the most cost-effective way initially, because you have to buy multiple pieces of machinery. But if you think about how long it takes to clean and take apart a mill, it may make a lot of more sense depending on the volume of material that you're trying to produce. So DSL or RS, which is the manufacturing scale, it's horizontal medium mill. Again, pass through a circulation mode. The integrated pumping and steering system is unique. We also have the ability to go up to 6,000 RPM, which will get us exactly to 10 to 16 meters per second of rotor speed. We can independently control our milling rotor from our pumping speed. Again, also on the horizontal medium mills, we offer ceramic, zirconium oxide, silicon carbide, different hard steel, whatever, for different applications. So there's a lot of new end-use markets like battery, hydrogen, you name it. They all require specific materials to be used inside of the mill, so not to contaminate or cross-contaminate the slurries. Depending on the screen size or dynamic gap that you're using, you have the choice of many different media sizes. And then there's also nano machines available, or even a nano kit that allows you to upgrade from a standard SL to a nano machine if you require super, super small particle size. We have the ability on the C technology kind of to control a lot of these parameters. So we have also what's called cutoff values. Just if the temperature is an issue, you have the ability to control that and set basically maximum temperature. Once that point is reached, the machine will either stop or run at a different speed or energy input. You also have the ability to program 2 separate warning stages that basically alert the user, hey, you're approaching 80C. You may want to be careful here. So maybe at 70C, you can set it up on at 75C, and then okay, we're almost at 80C, corrective action is needed. Otherwise, my milling process will stop or we run at a different speed. We can also set up different parameters. Again, I can set up a job parameter, give a product a color, a name, or a batch number, and then I can put in all the different values that pertain to this particular job. So, for example, if I want to run something with a certain speed or certain amount of energy, the right milling diameter, all these things I can program into my system to ensure that next time I'm running the same project, that I'm getting the same end result. I can also, with the C technology, do what's called a net power calibration. That could be interesting because when the machine runs without product, it's already basically showing a torque value and so on, because it's moving its own parts. And by doing a net power calibration, I can factor out those values. So when I look at energy input or torque value, then I'm looking exactly at the numbers that pertain to the processing of my material without the noise from the machine. That's what that does. Then we have really cool lab space. Obviously in Germany, a very high-end applications lab with many different dispermats, vacuum systems, dissolvers. But we also have a nice lab in Connecticut at Big USA. You can see a lot of different attachments. This is actually an older picture. We have newer models now, and we have a really cool lab with a lot of good capabilities. Here is the new Dispermat AE, and we have an SL machine in Wallingford. We also have a video that you can watch about our lab and the capabilities on a YouTube channel that we have. We can share that at the end of the presentation here. But that if you want to come up to our facility, please let us know. We welcome customers. We won't charge you for it if you come in for a day and want to explore the different types of equipment and also maybe run your product as a proof of concept to see, let's see how well does a basket mill, mill down my material compared to the 3-roll mill that we're using or a horizontal medium mill. Maybe I wanted to check out a rotor stator, so there's many different options that we can explore to help you pick out the right solution and equipment. And another big benefit is by having it at Big USA, we have the cooperation of our colleagues from the additive side to come in and give us really good, meaningful advice if we request it on formulation improvements and letting us know exactly, hey, this additive works really good with that base formula as a defoamer, for example, or as a wetting agent or dispersing agent. So there is many different additives that we can choose from that we have access to and will help you optimize the process and your formulas. So we don't want to come across as just a hardware supplier. We're really a full-turn solution provider to all your needs from hardware as well as the formulation side. That's what we bring to the table, and it sets us apart from the competition. And with that, we had an hour. I turn it over to John for questions, and I appreciate everybody that was on the call today.
Yeah, no one logged any questions, so I think we'll wrap up, but immediately following this webinar, you'll receive the link to the recording. If you do have questions, simply hit reply. It'll come to the marketing team and we'll route them to Andy or a member of his team. Thank you for joining us. Also, keep in mind for the dispersion deep dive that will be next Tuesday. Link is in the chat here. I'll leave it up for a bit, but you're welcome to join us then to learn more also. So thank you, Andy. Thank you, everyone, for attending. Hope you learned something. I always do. Andy, appreciate your expertise and insight into this. Thanks, everyone.
Thank you, everybody. Appreciate everyone on today. And maybe you come up for a visit to Wallingford. I'd love to have you.
Sounds good. Thanks, all. Have a great one.
Thanks.